Okay, everyone. In this video, I'd like to cover the second experiment, which is the separation of mixtures. So to get started, I'd like to think about a few things, a few topics that you probably talked about in lecture and are pertinent to this experiment, but I wanted to recap the main concepts. So the first question is, what is a mixture? Well, I think we all kind of have an intuitive sense of what a mixture is. A mixture is definitely the combination of more than one thing. And what those things are doesn't really make a difference. We just know that when you put two things together or more things together, that comprises a mixture. Now, in chemistry, we spend some time thinking about categorizing these mixtures. And one of the broad categorizations is whether a mixture is heterogeneous or homogeneous. Now, students tend to have some difficulty with this because they tend to think that being homogeneous pertains only to a very small subset or have certain requirements that are not necessarily requirements to be homogeneous. But let's kind of just start with heterogeneous because I think that's the one that's easiest for us to understand. A heterogeneous mixture is where the two components are mixed together, but if you look with a microscope, or even if the particles are big enough, if you look down at the mixture, you can start to pick out individual particles of different things. So for example, this would be like if you were to take some table salt and some sugar. Now it would be difficult to do this, but in theory you could. You could go in and pick out, after you mix those together, if you took some table salt and sugar and mixed them together, um, and you use a spoon to stir them up, you could go in and pick out sugar crystal from salt crystal, sugar crystal from salt crystal, meaning that you can go in and identify those individual little crystals and pull them apart and separate the mixture back out. That's what a heterogeneous mixture is. So something like soil is a heterogeneous mixture. You have many different components mixed together and it's not uniform necessarily, or you can distinguish the individual components at a macro or microscopic level. Now, how does this differentiate from homogeneous? Well, a homogeneous mixture is one where the two components are mixed all the way down to the microscopic level, and you can't go and look at it and separate the components. So what would be some examples of a homogeneous mixture? Well, for example, salt water. When you dissolve salt in water, if you look at that salt water mixture, you can't identify the salt crystals anymore because those salt crystals are now inherently intermixed with the water. The ions have separated and now the ions are mixed one-to-one with the water molecules. So that would be an example of a homogeneous mixture. Now, other examples of a homogeneous mixture, and this is where students tend to get a little bit confused because they think that because solutions is such an obvious, aqueous solutions are such an obvious case, that they forget that you can have other cases. Another example of a homogeneous mixture is air. So the atmosphere is a mixture of gases like oxygen, nitrogen, carbon dioxide, argon, and a variety of other gases, but at much lower compositions. Now, air itself is a homogeneous mixture, but if you look at clouds, this is an example of a heterogeneous mixture. So here we have air that has its components, but then mixed in with the air is water vapor, where we can go in and we can actually see that this water vapor is distinct from the air. So that's an example of where you have a heterogeneous mixture that consists of a homogeneous mixture and water vapor. The homogeneous mixture being the air itself, the nitrogen, the oxygen, and the argon. Okay, so now let's talk about physical versus chemical process. So it's important that you guys understand this, and in class you've probably gone over this in more detail, but in lab we are going to use both of these processes this semester, but in this particular experiment we're going to be doing all physical processes. So what is the difference between a physical and a chemical process? Well, a physical process results in a change where the composition of the material, meaning what the material is made of, doesn't actually change. So for example, boiling water, where we take water from the liquid phase to the gas phase, the material itself is still H2O, bound, the bonds are all the same, the material is the same, we're just changing its physical nature from a liquid to a solid. So phase changes are an example of a physical process. Another example of a physical process would be, like tearing a piece of paper. or breaking up some larger material into smaller material. The chemical composition of that material is staying the same, but we are changing its physical characteristics. So that's a physical process. And we're going to use several different physical processes in this experiment. So the ones that we're going to use are sublimation, which is a phase change where we go from the solid phase to the gas phase. We're going to be using dissolution. So dissolving sodium chloride into water is a physical process because we can evaporate the water and recover the sodium chloride. We'll see that today. Now, to contrast that, a chemical process is a process where the chemical makeup of the material actually changes. So, for example, if you take a piece of iron and you leave it outside and it rusts, the iron, which is pure iron, chemically changes to iron oxide, and now the material is a new material because it has chemically changed, meaning the bonds have changed and the composition has changed. So a chemical reaction is where you actually change the composition of the reactants in the products. And none of the processes we're going to be doing today are chemical in nature. They're all physical in nature. Okay, so in the separation of mixtures experiment, we have to talk about a very important couple of concepts that can be defined both in terms of words, but also in terms of mathematical definitions. So a percent composition, if we want to characterize a mixture is composed of several different things. A qualitative description of that would be the fact that you have more of one thing versus another. Qualitative means that you are giving it a sort of a quality perspective, but not necessarily a quantitative perspective. So if we want to quantify the amounts of something in a mixture, we use percent composition. And that is where we define that as the percentage of a component within a mixture. So the way that we would calculate this mathematically is we would take the mass of a given component divided by the total mass of the mixture and then multiply that by 100. So if, for example, we had 50 grams of sugar and 50 grams of salt, then the mass of the component, let's say sugar, would be 50 grams divided by the mass of the mixture, which would be the 50 grams plus the 50 grams, which we would then, when we do that division, we would get 0.5. We would multiply that by 100 to get 50%. So you can kind of see that this is a percentage based on the mass of a given thing versus the total mass of the mixture. Okay, so another thing that we're going to talk about in this experiment is percent recovered. So we're going to take a mixture and we're going to start to separate it. That's what we're going to do in this experiment. We're going to take a mixture of salt, a mixture of salt combined with ammonium chloride and silicon dioxide, so 3 components, and we're going to go through a series of steps to separate them into each of their individual components. So in the end, we want to figure out, well, after we did all these separations, how much did we get back in the end from what we started with? You can kind of think of this as like a yield from our process. It's the percent recovered. So what percent of the total initial mass do we recover after all of these steps? So to calculate the percent recovered, we're going to take the mass of the recovered components. So how much silicon dioxide did we get back? How much ammonium chloride did we get back? And how much sodium chloride did we get back? And we're going to sum those up and divide by the initial mass of the mixture. So if we get back 100% of the material, then the total mass of the recovered components will equal the initial mass of the mixture. And there are 2 possible outcomes here. We could get a percent recovered that's less than 100%, meaning we've lost some material, or we can get a percent recovered that's greater than 100%, meaning we've gained some material. And that's going to be something that you're going to have to think about. Where along the lines of this process might we gain some material that wasn't there originally? Okay, and then so the last one that we have to define is the percent gained or lost. So we know what the percent recovered is, and then the question is, well, can we redefine that as, well, how much of the material did we either gain or lose? So the way that we would calculate this is we would take our percent recovered minus 100%, which is what we should have gotten back, and then this will tell us our percent gain or lost. So if you do the math, if we got back 100% and we subtract 100% from that, we're going to get 0% gained or lost. That makes sense. Let's say we got back 95% recovered, meaning we lost some. So we kind of already intuitively know that what we lost was 5%. Now, the way that this equation works is if you take 95% minus 100%, we're going to get negative 5%. So the reason why we do this subtraction is because it gives us a negative sign when we've lost or a positive sign when we've gained. So this equation is going to allow you to calculate the percent gained or lost. Okay, so here's how this is kind of a flow chart that's going to take us through the various steps of our experiment. So our mixture that you're going to get, your unknown, is going to be in a vial, and it's going to be a mixture of ammonium chloride, sodium chloride, and silicon dioxide. It basically is a powder that has a little bit of a brownish hue, where you're going to be able to see some white little specks in it, and that's going to be the ammonium chloride and the sodium chloride. And then we're going to do some physical processes to separate them. So we're going to talk about each one of these in more detail, but I'm going to kind of just show you the flow chart. We're going to get rid of the ammonium chloride by heating it up and using the process of sublimation, where we take the solid ammonium chloride and we go to a gas. And we're going to remove the ammonium chloride by sublimation, meaning it's going to basically sublime into the gas phase and go away. So with the ammonium chloride, we're not going to actually recover that component. We're going to measure the amount of ammonium chloride by determining how much mass was lost. So we're going to measure the initial amount, we're going to sublime the ammonium chloride off, we're going to measure what's left over, and then the difference in mass is going to tell us how much ammonium chloride was present in the sample. So once we've done part A and we've gotten rid of the ammonium chloride, then we're going to do our separation. So we're going to have, what's left is going to be sodium chloride and silicon dioxide. Silicon dioxide is basically just sand. The sand that you would find on a beach is silicon dioxide. So you may hear me refer to silicon dioxide as sand. So one thing that we can take advantage of here is that sodium chloride is soluble in water, but sand is not. So if we add water to this mixture, the sodium chloride is going to go into solution, meaning it's going to dissolve as an aqueous solution, and the sand is going to be left behind because it's not going to dissolve, and we're just going to have sand that's left behind. So we're going to do what we call an extraction, and then from here, once we have the salt solution and the wet silicon dioxide, we're going to remove the water that we added, and we're going to evaporate that water off, and that's going to give us solid sodium chloride and solid silicon dioxide, which we can weigh and get the mass of those individual components. And at the end, we're going to have isolated NaCl and SiO2. Okay, so let's talk about how we're going to do that part A, the sublimation of NH4Cl. So now the most important thing with this experiment is that you have to weigh. We have to weigh everything, because what we're going to be doing is we're going to be doing a lot of obtaining mass by the difference of mass. So let me explain what that means. So what that means is basically we have glassware that's around, right? So in the first step here, we're going to place our unknown mixture into what we call an evaporating dish. That's this little dish here, and I have an actual picture of the evaporating dish in a couple of slides. Now, as we're going through this process, we have to know how much the evaporating dish weighs so that we can know what's happening with the mass changes of the things that are inside of it. So weighing by difference means that we weigh the evaporating dish, with something else that's in it, and then through subtraction we can get the difference in mass, which will tell us the mass of the mixture or the mass of the ammonium chloride that was sublimed off. So it's important that we weigh at every step in this experiment. So here's what we're going to do. So in lab, you would make sure that your unknown is thoroughly mixed. Basically, you'd get your unknown in a vial, you'd shake it up and make sure that everything is uniformly mixed together. And then what you're going to do is you're going to take an evaporating dish, which looks like this, and I will show you a picture of it in a few slides. You're going to put it on a balance. So again, we have our analytical balance that we learned about in the first experiment. And we're going to have turned this on, hit the 0 button, and then we're going to place our evaporating dish on top. And the reading that we're going to get is 30.4740 grams, which you write on your data sheet. So now we know how much the evaporating dish weighs. So you're going to add the unknown mixture into the evaporating dish, and you're going to determine the weight of the dish and the mixture. And you're going to get 33.7043 grams. So now you can see that the mass went up because now we have the dish plus the mixture. So when we subtract the dish away, we can figure out how much mass was the mixture, how much mass constituted the mixture part of those two things. So by subtracting the 33.7043 from the 30.4740, if you just do that quickly in your head, you're going to see that we put about 3 grams of the unknown, or 3.3 grams of the unknown, give or take. You're going to have to actually do the calculation yourself. And then there's going to be an apparatus set up in the hood. And the apparatus that's going to be set up in the hood is going to look like this. This thing with this pole that's sticking up on this frame is called a ring stand. So you're going to have a ring stand that's there, and then you're going to have a ring. Basically, there's this this metal ring that attaches to the ring stand, and on top of that, we're going to put a clay triangle. And what a clay triangle is just a piece of it's just a couple of pieces of wire that's in a triangular shape, and there's just some clay O-rings that go around the metal. And what this does is this just basically holds your evaporating dish. So and then underneath it, we're going to put a Bunsen burner, and the Bunsen burner is what we're going to use to heat this up. So this would be set up for you in the hood. It would look exactly like this. The only difference is during the sublimation step, we're not going to use a watch glass. The reason for that is because we want the ammonium chloride to evaporate off into the air. And then so we're going to heat this up, and we're going to allow the mixture to sublime. And as it's subliming, we're going to shake the mixture gently. And that's just to make sure that all the ammonium chloride can come off. Now here's what this would look like if you were in lab. So when you put this on the heat source, you would see the ammonium chloride coming off as these white vapors. This is exactly what we see when we do this experiment. So what's going to happen in those steps is the ammonium chloride plus the sodium chloride plus the silicon dioxide. This is our mixture that we're going to have in there. This ammonium chloride, as we heat it up, is going to go to ammonium chloride from solid to gas. That's what subliming is. And so effectively, we're going to remove that and be left with the sodium chloride and the silicon dioxide in the evaporating dish. This little delta here symbol indicates that we're heating. That's what that means in the reaction. So in essence, if we were to boil this reaction down, we're going from NH4Cl solid to NH4Cl gas. Okay, so once we've done the sublimation, we'll know that the sublimation is complete once we no longer see the white vapor coming from the sample. We're going to take it off and we're going to put it onto some wire gauze to cool. The reason why we put it on wire gauze is to prevent the Erlenmeyer the evaporating dish from cracking. There's a process called thermal shock, where if you take something very hot and you place it onto a cold table, it cools down so quickly that it actually causes the material to be put under a lot of stress, and then that stress can cause it to crack. That's called thermal shock. By putting it on wire gauze, this kind of lifts it up off of the table and allows the evaporating dish to cool a little bit more slowly. So that's why we do that, to prevent thermal shock. And then you're going to weigh the cooled sample on the analytical balance, and you're going to obtain a weight of 33.5350 grams. So now let's just take a look at the data sheet. So we started with our evaporating dish with nothing in it, with 33.4740 grams. We added our original sample containing all three components, and we get a mass of, oh, I think I have to fix that. So so I have to fix this. I'm sorry. This should have been 30.4740 grams. Your data sheet will be corrected. So in this case, just know that this should have been a 30 and this should have been a 33. I will correct that on the data sheet. So we've gone up by approximately 3 grams in terms of mass, which means that our sample is going to be the difference between the 33.7043 grams and the 30.4740 grams. So by taking this difference, we can get the mass of the original sample. Now what you'll notice is that the mass of the evaporating dish after subliming has gone down a little bit. So when we sublimed, before we started subliming, we started with 33.7043. Now we're at 33.5350. So our mass has come down, meaning we lost a little bit of the NH4Cl. So what you can do is you can take the mass of the 33.5350 and subtract the mass of the evaporating dish, and then the difference between that mass and the original mass should give you the mass of the NH4Cl. In essence, you're calculating the mass difference from the mass of the evaporating dish in the original sample minus the mass of the evaporating dish after subliming the sample. So the difference between these two weights is what was lost, and therefore is the mass of the ammonium chloride. And then you can calculate the percent of the ammonium chloride by taking the mass of the ammonium chloride divided by the original mass times 100. So that's our percent composition calculation. Okay, so now let's look at the second part of this. So what's left in our evaporating dish? So now that we've heated off the ammonium chloride, what's left is going to be our sodium chloride and our silicon dioxide, or our sand. So that's going to be sitting here in our evaporating dish, waiting to be separated. So now what we're going to do is we're going to do a process called extracting, where we're going to take the NaCl and we're going to dissolve it into an aqueous phase, or into a water phase, and separate that from the sand. So to do this, we're going to have two different containers. The evaporating dish is going to be our container for the sand, and a 250 milliliter Erlenmeyer flask is going to be our container for the sodium chloride solution that we're going to make. So again, we have to weigh our 250 milliliter Erlenmeyer flask, and the reason why we have to do that is because in the end we're going to have our sodium chloride in here. So we have to know how much the mass of the flask is in order to get the mass of the sodium chloride. So we put that onto the balance and we get a mass of 92.0031 grams. Then what we're going to do is we're going to have, to our mixture, we're going to add 10 mils of water and we're going to stir. So you have your sodium chloride and your sand in here. You're going to add the water and you're going to stir it up. And the sodium chloride is going to start to dissolve. So the sodium chloride is going to go into the water phase, leaving the sand behind. And we're going to make sure that we stir for 2 to 3 minutes, because if you tried, in this previous experiment, if you tried to, when we did the egg experiment in experiment 1, if you tried to dissolve salt in water, you see that it takes some time for the salt to dissolve all the way. So what we're going to do is we're going to do a process by which we're going to slowly add the water, and we're going to stir to make sure that we get all of that sodium chloride dissolved. And then we're going to do a process called decantation. So if you notice, this little evaporating dish has this little pour spout. What we're going to do is when we decant, we're going to basically pour off the water part into the Erlenmeyer flask very carefully, and so that we don't lose any of the silicon dioxide. So we're going to leave the solid behind but pour the liquid phase off. And that does take some practice when you're doing it in the lab. And then what we're going to do is we're actually going to repeat this adding water, stirring, and decanting step, so steps 2 and 3, 2 more times. And what we're doing is we're adding water and then we're pouring it off, and then we add some more water, so if there was any salt that was left behind, it gets dissolved and washed away. And then doing it a third time, we make sure that we get any very, very small residual that was left behind off. This is called washing the sand. We're basically washing the sand and removing all of the salt. So in the end, we're going to have 30 mils of water in here that contains all of our salt, and what we're going to be left with is just some wet sand in here. So you can see that we'll have wet sand in our evaporating dish, and we'll have our aqueous NaCl phase in the Erlenmeyer flask. So now the next thing we have to do is we have to remove the water from both of these. So you're going to set up your ring stand. Again, this is what it's going to look like. You're going to have your vertical riser. You're going to have your ring coming off that's attached to the vertical riser. And then here you go. Here's a picture of the wire gauze I was telling you about. So you can see it's literally just wire, and it's kind of in a mesh, and it's going to hold up our Erlenmeyer flask. But we also use wire gauze to put hot things down on the table or on the bench. Okay, so heating this up, we're going to use a Bunsen burner to heat this up, and we're going to boil the water off. So we set up our ring stand with the wire gauze and the Bunsen burner. You're going to heat the Erlenmeyer flask until all the water is boiled. And whenever you're working with a Bunsen burner, you have to have somebody physically standing at the bench top watching it, because obviously it's a fire hazard. So once all the water is gone, and we make sure that all the water is gone by even heating up the neck of the flask to get any water vapor that's off. Because if we leave any water behind, that is going to be counted in the mass, but not necessarily from the original mixture. So we have to make sure that we get rid of all the water, or else it could lead to an error at the end of the experiment. So once we've gotten all the water off, we weigh the Erlenmeyer with the salt residue, and we get a mass of 92.2445 grams. So if we go to our data sheet, you're going to notice that we had 92.0031 grams. That's the empty Erlenmeyer flask. After we add our salt and dry it off, we get about 0.2445 grams of the NaCl. It's not exact, but you can see that when you subtract these two numbers, we're going to get about 0.2 grams of the NaCl. So that's what you're going to do. You're going to subtract these and get a mass. And remember, at all times when you're doing your subtractions, you should be subtracting considering the significant figures. So the last thing we're going to do is we're going to look at the percent of NaCl, and we're going to calculate that. Oops, and I made a little mistake here. This should be the percent of NaCl is equal to the mass of the NaCl divided by the original mass. So we're going to calculate our percent NaCl by taking the mass of the NaCl over the original mass that we had. Okay, and then the last step is we also have to dry the sand off. So there was a little bit of water on the sand that we have to get rid of, or else that water will get counted into our mass. So in this case, we're going to set up our original setup. We're going to have our evaporating dish, clay triangle, and our Bunsen burner. And then this time we are going to cover it with a watch glass. So we have to go to the balance and weigh out our watch glass. And the reason why we have to weigh it out is because in the very end, we now have three components that we have to account for. We have the evaporating dish, the watch glass, and the sand. So if we want to get the mass of the sand, we have to subtract away the mass of the evaporating dish, which we did at the very beginning. We have to subtract away the mass of the watch glass, which we just are going to do here. And then what's left behind is the mass of the sand. So we're going to weigh out a watch glass. We're going to cover our Erlenmeyer flask with it, and then we're going to start to heat. Now, the reason why we do this, the reason why we cover this in this case is because when you heat up the sand, it tends to pop, meaning the little sand particles will tend to pop out as they dry. And if we did that, we would lose sand, meaning the sand would pop out and come out of the evaporating dish, and then it wouldn't get counted at the very end. So we put the watch glass on just to make sure that any sand that pops up gets caught by the watch glass. And then all the water that evaporates is going to come out through that little pore spout, and we heat until we don't see any condensate anymore, any liquid water around. So once the dish is fully dried, we're going to cool it on wire gauze until it comes down to room temperature, and then we're going to weigh the evaporating dish, watch glass, and sand and get a mass of 48.3124 grams. So what you're going to do is you're going to pull your mass of the evaporating dish. I gave that all the way up to you on line 1. We have the watch glass also, which we just measured. So we're going to add those two masses together, and that's going to be the mass of the evaporating dish and the watch glass. So we'll add 11 and 12. And then the difference between line 13 and line 14 is going to be the mass of the sand, right? So whatever is additional mass in terms of the mass of the evaporating dish, watch glass, and sand, minus the mass of the evaporating dish and watch glass is going to be the mass of the sand. So that's how we're going to get that. And then again, I made a mistake here when I was copying and pasting. So the percent of the silicon dioxide is going to equal the mass of the silicon dioxide divided by the original mass. So we'll go right back to the beginning to see what our original mass was. So that's going to give us our percent for the silicon dioxide. Okay, so the last part of the data analysis is to look at the percent recovered and to look at the percent gained or lost. And we're also going to do two little bits of error analysis. So if we want to figure out the percent recovered, we need to know what was the total mass of the recovered components divided by the initial mass of the mixture. So we have the initial mass of the mixture. That's the original mass. And then you have to go through and you have to look at, well, I calculated a mass of the ammonium chloride, I calculated a mass of the NaCl, and I calculated a mass of the SiO2. So we're going to add up all the things that we recovered, and then we're going to divide it by the original mass. And then that's going to tell us how much we recovered. So we're going to write that percent recovered here. And then you'll get the original mass from line 3, and then the mass of each of these from the different parts, A, B, and C. So in this particular experiment, we're going to find that the percent recovered is less than 100%. This particular group was pretty good. They did a pretty good job. You'll calculate the number of what they actually got, but it's not going to be 100%. So you're going to then calculate your percent gained or lost using the equation that I have over here. And now what I want you guys to think about is what experimental errors might have resulted in this percent recovery. So if we have a 90, I'm just making up a number. Let's say it's 90% recovered. That's not the actual number, but let's just say it was. I want you guys to think about where along the experiment might the student have made a mistake that could have caused this. So give me 2 places in the experiment where a student might have made a mistake. What would have been the mistake? And then how would this have thrown off the final result that we didn't get back 100% of the material? And then I also want you to think about how could we get a percent recovery that's greater than 100%? So this happens all the time. You might think it would be impossible, but it happens a lot. We see it all the time in the actual lab. And there's a very specific reason why you would get a percent recovery greater than 100%. So in essence, you have to think about where could we be gaining mass that wasn't there originally. So you answer these 2 questions. Just a few sentences is fine to explain your thinking, and that will also be incorporated into the data sheet. Okay, so one thing that I'd like to point out is what are we thinking about in terms of safety? So one of the components that will be a part of the quizzes and the exams in the lab is thinking about what we have to do for safety. So you actually took a safety quiz already in mastering, but I want to, in all of the experiments where we need to think about safety, I am going to point out the safety to you anyway, because you should be thinking about this as you develop experiments. So in this case, you need to have your safety glasses and lab coats on at all times. So if you were doing this experiment, you would have to have those on at all times. The reason for this is because when we heat things up, things can react unexpectedly and they can react violently. So, if your evaporating dish has a stress fracture, you begin to heat it up, it may crack or even explode. That's fairly rare to happen, but it could. And then you have, hot pieces of the ceramic that kind of fly around. So that's why we wear safety glasses, and to make sure that anything, as we're heating, that bumps out of the experiment doesn't go into our eyes. In this experiment, we have to always be cautious for broken glass. It's very common for students to break glass. If you were to break glass in the lab, you would let us know. And then it's very important that you let glass cool before you try to clean it up, right? Because a lot of times we're heating things up on the Bunsen burner, and it may even break while it's on the Bunsen burner. So if that happens, we have to wait for everything to cool down, shut the Bunsen burner off, and then we can go in and clean it up so that we don't get burned. And with flame safety, you want to make sure that your hair is always tied back if you have long hair. You want to make sure that if you have long sleeves or baggy clothing, that those are pulled back and away from the flames. And it's always important that one person must always be present when a Bunsen burner is on, physically watching it. That's to minimize fire risk. And just to kind of give you an anecdotal story about this, so I always tell my students this, and I'm shocked when they do things. So objects heated with a Bunsen burner are hot, don't touch. So in several instances, I've had students do this. In one instance, I had a student try to take a evaporating dish off of the Bunsen burner with their hands. So they didn't get very far. They touched it a little bit, and they realized it was very hot. And then they knocked it off, and it broke into a bunch of pieces. And then the student looks at me, and I looked at the student, and then they immediately go to try to clean it up, and then they go and they touch the hot pieces of ceramic again. So, it's always important to be cognizant of the fact that when things are hot, they're going to be hot for quite a while. So, don't touch them if they're hot. Okay, so this is the things you need to know for experiment 2. We are going to, you guys can work on the data sheet and upload it when the at the date and time that the syllabus says to upload it. And if you have any questions, you can always email me or stop in during my digital office hours.